And we're finally ready to take a closer look at the hole, what's called the hole in the ozone layer. And I think what we've recognized by now is that the hole is a region over the Antarctic that has a much lower ozone concentration than the rest of the world. So we want to take a closer look at that and understand why it happens. Is it permanent? You know, that sort of a thing. So as it turns out, there are extreme weather conditions at the poles. And this graph here shows the temperature at the poles, at the Arctic and the Antarctic, going from May through October. In the middle there, July and August, that's what's considered the winter in the Antarctic winter. And then up here, the months are different because it's showing the Arctic winter, which is January, February. All right, the Arctic winter is the northern hemisphere pole, and the Antarctic winter obviously is the southern hemisphere pole. So the seasons are opposite. So anyway, what you see is that the Antarctic is colder than the Arctic, and there is a situation. Well, I'll explain this graph real quick first. The blue line is the average temperature at the Antarctic, and the red line is at the Arctic, and then the shaded regions are showing the range in values over time. But anyway, there's a line here, and this line says Psc Formation Temperature, and what the Psc stands for is Polar Stratospheric Cloud. Okay, Psc stands for Polar Stratospheric Cloud. All right, I'm going to change pens. Polar Stratospheric Cloud, in case you can't see the red pen. And below this temperature, there is the possibility of the formation of something called a polar stratospheric cloud, which is a very thin cloud in the stratosphere. And because it's so cold, instead of being little drops of water, it's little drops of ice. All right? And there's something important about those little drops of ice that occur. Okay? And also, notice that the little drops of ice can only occur below this temperature, and so there's a range in time when that can occur, and it happens for a longer period of time and more often in the Antarctic than the Arctic. See, there's a real wide band here. Sometimes in the Arctic it doesn't get cold enough to make polar stratospheric clouds, but always in the Antarctic it does. It's colder down there. All right, and so what happens is those polar stratospheric clouds provide a surface for which chemical reactions to occur that wouldn't normally occur. All right, and so what happens is because they are little bits of ice, then it's little solids, and the little ice crystals that form these polar stratospheric clouds. Not only is it different than a regular cloud, but during the Antarctic winter, the winds that normally circulate around the entire world do not circulate around the Antarctic polar region. So the clouds that are up there stay pretty much the entire Antarctic winter. They don't get blown away. They stay. So you've got these sort of stationary, unusual, very high, very cold clouds that are bits of ice. And those clouds contain various other compounds. It's not just ice, but various other compounds that are in the atmosphere get frozen onto and into those little bits of ice. And for example, the ice crystals clouds contain what normally, under normal conditions, these compounds would be relatively stable in the stratosphere, holders of chlorine depositories. Those are normally pretty stable. Once a chlorine atom gets bound up into one of these molecules, normally it's not going to break because the ultraviolet light isn't enough. But because of the surface of the cloud, it almost acts like a catalyst and allows the chlorine to be broken off. All right, well, not until it gets sunny outside. So what happens is these compounds, which under normal conditions are pretty safe depositories of chlorine, will be attached to those polar stratospheric clouds. It sits there pretty much all winter because the clouds stay put. There's no sun. It's dark, so there's no ultraviolet light to break any bonds or whatnot. Normally, anyway, the bonds would be broken by ultraviolet light because they're too strong. But once the sun comes out, and it's still very, very cold in September, if you look back at this plot here, in September, it's still very, very cold. You still have, in the Antarctic, you still have the appearance of these polar stratospheric clouds, but the sun's coming out. So you've got a solid surface with these molecules stuck to it, plus the sun coming out. So then you have the presence of the clouds and then ultraviolet light. And what happens is these bonds are broken, and this bond will be broken here, and this bond will be broken here, and you end up producing all at once a whole bunch of chlorine atoms. Okay? And so those chlorine atoms then, as the clouds start melting, the ice crystals, as it warms up, those chlorine atoms are released, and they interfere with the natural ozone-oxygen cycles and start removing ozone from the atmosphere in that region. There's still not a lot of wind blowing around, so there's not a lot of diffusion where these chlorine atoms can be blown away. So right at the surface there, where these chlorine atoms are being, the surface of the stratospheric clouds, where these chlorine atoms are being formed, then they will, interact with the ozone, and through a series of, complicated reactions that we talked about before, end up breaking the ozone down to oxygen. All right, so that's why we see this dramatic decrease in ozone concentration in the Antarctic spring. Sometimes if it's really cold in the Arctic as well, and the stratospheric clouds, frozen clouds stay longer, you'll see a similar effect in the Arctic region, but it normally is not cold enough, long enough for that to occur. So this is why we have a seasonal fluctuation in ozone concentration, and this is why we have the hole in the ozone layer. Now, once things warm up and the winds start blowing down into the South Pole region, the Antarctic region, then the hole shrinks. So the hole gets bigger and it gets smaller based on the wind patterns and the season. But what happens then is the overall effect on the global ozone concentration is that it will reduce the overall global ozone concentration, because if you have regions of very, very low ozone, and then you have the winds, stratospheric winds blowing things around again, then the net effect is going to be an overall decrease in ozone concentration over time. In ozone concentration. Okay? Worldwide. All right, so that's what the ozone hole is. It's a seasonal effect, and you saw evidence before that over time, the minimum concentration of the ozone in the Antarctic has continued to go down. And so scientists have definitely correlated the decrease in the ozone concentrations at the South Pole with the increase in the chlorine, and the chlorine is definitely coming from CFCs.